Hi, my name is Junwei, and thanks for watching this video. The title of this presentation is Quantifying Reservoir Stimulation Using Passive Travel Time Tomography. This is a pilot study. We collaborated with BGP on a tight sand reservoir stimulation project in China. Estimating reservoir stimulation volume takes a lot of time and information. And in this talk, I just want to show you how passive travel time tomography can add a few extra but critical pixels in the big picture. First of all, why passive tomography? Well, as rock deforms, part of the energy is carried out by seismic wave, just like the thunders carrying out the energy produced by the lightning. Upon we hear it, we check the time, and we know the location of the source. And the source region identify the area where the energy is beyond the threshold. So if we have enough lightning, not only the source region, but maybe the entire sky, the skyline will be illuminated. And the same applies to microseismics. When it occurs, it lights up the rock as well. And passive travel time tomography is such a technique to image part of the Earth illuminated by the seismic waves. Travel time tomography usually takes two steps. The first step is to calculate the travel time based on your initial model. And the second step is to update your velocity in order to minimize the differences between your prediction and the calculation. In our case, we use the fast sweeping method to calculate the travel time. It's simply a finite different method of solving the Econo equation for the travel time field. And we use the so-called adjoint state method to update the velocity. Unlike the other method, invert a huge matrix directly or indirectly. The adjoint method formulate the inverse problem as a optimization problem under the constraint of the partial differentiation equation. In other words, it converts the inverse problem to another forward problem, which can again be solved by the fast sweeping method efficiently. We validate this technique on synthetic data, a well-controlled numerical experiment, and then we apply that to a challenging data sets from a tight sand reservoir stimulation project. The geology there is complex, the azimuth coverage is limited, and even the P wave first arrival is not even visible. But even so, the travel time tomography based on the direct shear wave still managed to recover part of the reservoir. And I also include a bonus slides from a different case mining site. The geology there is as complex as the tight sand reservoir, but because of the wider azimuth coverage, the tomography better recovered the degraded rock volume much better. I include this here just to give you more confidence in this technique, and then I'll draw some conclusions. So first of all, calculating the travel time using fast sweep method. As I said, it's just a simple finite different method. Idea is simple, the implementation is simple. It's just in C++ language, it's just a few for loops. So if you already know it, bear with me for a second. Use 1D as example. Point source is located at the center. The travel time there is 0. The rest point has no travel time, so the value is infinity. The fast sweeping method goes like this. It starts from one point, sweep along one direction, using its neighboring point to calculate the travel time at the current points. And of course, those points has no new information till you reach this point. This point is updated by the point source, and those points will be updated one by one because we are sweeping in the direction as the information flow. And then we sweep backwards, and those points will be updated. As you can see, 1D model takes 2 sweeps, and 2D will take 4 sweeps, and the 3D will take 8 sweeps. Each sweeping is independent on each other, so it's easy to parallelize this method on multi-core CPU. And fast sweeping method can not only apply to isotropic velocity, can also be applied to anisotropic velocity model. Here is example from isotropic heterogeneous model. You can see a strong contrast between low velocity and high velocity, as well as a significantly low P wave velocity here, and a 0 velocity here is like a cavity in the space. Using fast sweeping method on a single core CPU, it takes less than 5 seconds, I think it's about 1 second, to calculate the travel time on 10,000 grid points. The P-wave travel time field is plotted in isosurface, so you can see the wavefront is propagating away from the point source here. and it can take care of the low velocity and the barriers, which is the cavities, straightforwardly. If you still need the seismic ray parameters, you can trace the seismic rays, start from any receivers, following the gradient of the travel time, and you get the seismic rays. And of course, all rays ends at the source location. Another example from homogeneous orthorhombic velocity, the wavefront of the fast shear wave is not spherical anymore because of the anisotropy here, and it takes about 30 seconds to calculate the travel time for 100,000 grid points. So it's very efficient. The next step is to update your model. We form the objective function like this under the constraint of the Econo equation. So this is the general description for the Econo equation. T is the travel time at the location X. C is the propagation speed for P or for S wave. Omega is your modeling area, and gamma is the boundary. If it's a point source, the gamma is just a point, and the travel time at this point is 0. The objective function is defined as the differences between the calculated travel time and the observed travel time. So to optimize or minimize this objective function under an equal constraint, the usual way is to use a Lagrangian lambda variable, lambda times the left-hand side minus the right-hand side, and add this term back to the objective function to form a new objective function without constraint. And then we don't want to directly evaluate the variation of E with the variation of C because it's computationally prohibitive. With that in mind, and after some algebra, we end up with a new partial differentiation equation. It's an equation about lambda. So if lambda is satisfying this equation in the model region and satisfy this condition at the edge of the model, then the velocity perturbation can be calculated from lambda, and that velocity perturbation is ensuring the decrease of the objective function. It's very easy to verify. Just plugging this back into this expression, delta E is negative. And then we can use a step size times the model perturbation and use that to update the current velocity, and we repeat this iteratively. If you are using a steepest descent method, the model perturbation equals to the velocity perturbation. If you're using some other method like conjugate gradient or quasi-Newton method, and delta M can be calculated from delta C. In our case, we use a quasi-Newton method, limited memory BFGS method. And here is example from the adjoint method. A point source right here is surrounded by 6 receivers. The true velocity is 3 kilometers per second, but we use a 2 kilometers per second as the initial velocity. After one perturbation, delta C is plotted like this in 3D in isosurface, and in color density from viewing from the side and viewing from the top. So you can see that the joint method is consistent with the ray coverage. It shows the ray coverage in space and also shows the value along the ray shall be increased. The delta C is always positive. So you can imagine after multiple iterations, it will converge, and only those regions covered by the rays will be increased from 2 kilometers up to 3 kilometers. So this example shows us the adjoint method is adaptive to the ray coverage. It allows us to include model region, the regions in the model without the constraint of the data and without introducing stability issues. And then we integrate the faster sweeping method and the adjoint method in a 2-loop workflow. The first loop is only using the faster sweeping method to invert the origin time as well as to relocate the event's location. And then the second loop is to use the both faster sweeping method and joint method to update the velocity till it is converged. And we repeat loop 1 and loop 2 iteratively till the overall reduction of the objective function becomes marginal. And then we consider the tomography is converged in output result. So we apply this workflow to a numerical experiment with a single ball hole. The true model has 5 multiple layers. I think it's more than 88 layers. The monitoring ball hole is located at one corner of the model with 21 3-component geoforms. They are 200 microseismicity events modeled around the center of the model in this X and Y direction, thus mimicking a fracture is growing in XY direction because of the treatment at the center of the model. The source mechanism is just a random combination of explosion, double couple, and the CLBD. So we solve the full wave equation for all 200 microseismic events and merge the waveforms into multiple data files, just like the data files we recorded in the field. And then go through the basic processing first using our software called Insight. So the first step is the routine step, events detection. Detect the waveform that is beyond the threshold, and then save that part of the waveform as a triggered event, and then go through a manual picking for the first P and S arrival, followed by a manual check, and then use the grid search to locate the events. Very basic, and the velocity model we use is as using a homogeneous velocity. So you can see after the basic processing, we locate all 200 events, and most of them, I think more than 90% of them are located in the red box, which they're supposed to be. And if we're looking beside, this is the top view. If we're looking beside, it has a very good vertical resolution with only a single ball hole. And then we use the located events and the homogeneous velocity as the initial model to our two-loop workflow. After 3 iteration of the big loops, relocate all the events and also get a tomographic velocity image. It's easy to verify that the values of the tomographic velocity at the ball hole location is consistent with the well logs. It also recovers the velocity in the source region. Around here, the high velocity here is where the source is concentrated, distributed. So we also recover the velocity in the source region, which are supposed to be lightened up by the microseismicity. The error is quantified in terms of histogram. You can see from most of the events, the error in the origin time is less than 5 milliseconds. So this is 5 milliseconds. And the error in the location is less than 40 meters. And there are a few outliers exist, as you can see here. That's because they're introduced in the initial model, and because of they're far away from the true location, they're trapped in the local minima. And we also see that those outliers won't affect our tomography. And this is actually good because in the field, we don't know which events are outlier, which are not. We only know some minor events are far away from the majority. So if those are the definitions of outliers, then we can just say, those outliers doesn't matter. It won't affect our tomography. So you will see that case in a later case study. As a quality check, we calculate the travel time using the tomographic velocity and compare that with the observation. The differences shows almost a Gaussian distribution with a zero mean, and the standard deviation is 0.4, 0.5 millisecond, and I think it's already below the error you may introduce in the time picking step. So we apply that to a high-sand reservoir stimulation project. The treatment well is at the south. The monitoring well is at the north, 450 meters away, with 11 3-component geofoam at this location at a similar depth as the perforation shots. And there are 2 stages were performed. In this case, the black box marks the size of the tomographic velocity, 600 meters along east and west, 500 meters in the rest direction. The grid interval is 2 meters. The red dashed box is the search volume. Within this volume, we performed the grid search to locate events. The well logs, the sonic logs from both the monitoring well and the treatment well are available. But in our calibration step, we found the travel time based on the homogeneous velocity, based on the well logs, can match the perforation shots better than the layered model based on the well logs. Therefore, we decided to use the homogeneous velocity as to locate the events, and also use the homogeneous velocity as the input for the tomography. Once the event is located, we can plot up the predicted arrival, the blue dashed line, with the waveform. So this is a sample waveform from these data sets. You can see, recognize shear wave arrival, but it's hardly to say where is the P wave. You have to guess, and people may disagree. So this is common in these data sets. Now, because of the error in the location and the error in the model, the predicted arrival cannot 100% matches the waveform. So we use a cross-correlation method to refine the arrival, and then use the differences between the predicted arrival and the refined arrival to update the location as well as the velocity. The cross-correlation is done in a semi-automatic way. The details is in this paper. And according to the authors, it can save up to 80% of the analyst's time independent on the number of traces. So after 3 iterations of the big loop, the square root of the objective function reduces from 4 milliseconds to 1 milliseconds. Further iterations is only going to reduce that by 0.5%. So we consider the tomography is converged. So the result is plotted here, looking from the side. Z is vertical, pointing downward, and B and C are top view over the depths of stage 1 and the depths of stage 2. The dots or the spheres are the relocated events. The color associated with this origin time, white is early, black is late. The isosurface as well as the color densities shows the recovered tomographic velocities. Those events are probably outliers because they're away from the majority there, but we already know those won't affect the tomography, so we include those events in the tomography. Again, it's easy to verify the tomographic velocity value at the borehole location is consistent with the well logs. And there are 2 to 3 low velocity zones that may be associated with the treatment, maybe just the background velocity. As you can see, the velocity zone at the C and velocity zone at 2. The ray coverage is high, close to the borehole, and getting less and less as you move away from the borehole. Therefore, the resolution here is low. Although the low velocity is only recovered close to the borehole location, there's no reason to assume that the low velocity is only around this area. It's probably, start from the treatment. It's probably just the background velocity. But it gives us more information about the velocity, and that velocity model can help us for any further processing and any further stage locating project. And again, this is a shear wave velocity, which is more sensitive to the fluid in the pore space than the P wave velocity. As a quality check, we plot up the predicted arrival with the observation, and it shows a Gaussian distribution with almost 0 mean and 0.8 standard deviation. The difference between each pair's receiver and the source is so small, so if we plot the calculated with the observed occurrence time in the scale of hours, they matches very well. So this is just a 3D picture showing you a 3D structure of the recovered tomography velocity. As I said, the events are sparse and they're only located by shear wave. Those events are probably outlier because they're minorities away from the entire group. The resolution is high close to the borehole location, and the resolution is less as you move away from the borehole location. But there's no reason to assume the low velocity only occurs in those regions. It's probably a layer. It's probably introduced by the treatment. It's probably just the background velocity. But this velocity model going to help us for any further processings in the project. So this is the challenging data set, with the sparse events. And the bonus slides I want to introduce is from a mining site. The gray is the ore body, and this is the tunnel. And the microseismic events, about 80 events occurred, well concentrated around this area, and has a wide azimuth coverage provided by 27 three-component geophones, well distributed in 3D. And tomography well recovered low velocity because of the treatment. The undercutting is here. In my understanding, is just gonna lose the object, the rock here, and let the ore body collapse, and then move the mines out through the tunnel. So you can see the undercutting introduced a lot of microseismicity here, which significantly degrade the rock volume, so it shows as a low velocity. And this high velocity inside our body is likely because of the stress concentration there, so you increase the velocity. Velocity difference is huge. In this case, 4.2 for the high velocity, about 3 kilometers for low velocity. If I flick back and forth, you can see the degraded rock volume is much better recovered using this technique. So we have developed the efficient travel time calculator using a so-called fastest sweeping method, and then use the Adjoint method to update the velocity. We validate these techniques on a well-controlled numerical data, and we demonstrate its performance on noisy and challenging data sets. A better data, as I also show you, will give you a wide avenues. In a borehole situation, if we have two monitoring boreholes, that will improve the situation a lot. So finally, I guess the takeaway message is seeing is believing, and don't just listen. Thank you for your attention.